out these wonderful training sessions. So over to you, Dr. Qammer.
Thank you so much. Assalamu alaikum, everyone. And I would like to sincerely thank Professor Aqsa Shabir for her very kind introduction. And I'm so thankful to her for inviting me to deliver some of the exciting work, futuristic work we are doing here. And also I would like to thank British Council for funding these kind of activities in Pakistan, #1 university for women, which is very important. And I personally got opportunity to visit Lahore College Women University a couple of months ago, and I was so much impressed by the energy I see there. And I think you are the real world changer. So thank you once again for inviting me. Whatever I'll be presenting today will be, the purpose of training is to give some of the futuristic directions where students, academics, researchers can research over next 5 to 10 or 20 years. So my talk is not very different from that. So it will be some of the things which might not make sense at this stage, but trust me, they will be part of our life in future. So I'm sure all of you know that we are in era of digital technologies. So everything around us is digital. We ourselves are digital as well. And we have mobile phones, a technology and an asset which every one of us is using. And social media, which is enabled by this mobile phone, and then internet, of course. I'm sure I have an assumption that all of you have heard about 5G, because many of the phones in Pakistan and many of the service providers claim that they are providing 5G. So today I'll be talking about our next wave, which is beyond 5G, which will be 6G. And what is 6G and what are the enabling technologies for 6G? So this is what I'll be talking today. So please feel free to interrupt me if you have any question, or if you do not want to interrupt, let's keep all questions saved to the end. So you can type question in the chat and I can reply to those questions at the end. One humble request, could you please mute your mic when you are joining? If someone else is joining, Dr. Aqsa, aap jo hain wo co-host bhi hain, so you can mute people who are joining. So before going in detail about the talk, so I would like to tell you that I am from University of Glasgow, which is home to various Nobel laureates, including James Watt. I'm sure all of you have heard his name. John Logie Baird, who made television. William Thomson, the unit of temperature, Kelvin. So it's after William Thomson. And then there are so many discoveries where University of Glasgow is involved, including the Nobel laureate for recent gravitational waves and chemistry. They were the alumni of University of Glasgow. And University of Glasgow, if you don't know, it's the 4th oldest university in English-speaking world, established in 1451 after Cambridge, Oxford, and St. Andrews. And it was Scottish University of the Year as per Good University Guide 2022, and it's World Top 100 University. And I belong to Communication Sensing and Imaging Group, which I joined 5 years ago. And we started this group headed by Professor Muhammad Ali Imran, and we have grown significantly from 5 to 140 members in just 5 years. And I'm so proud to say that we have around 30 PhD students and postdocs from Pakistan in our group who are doing excellent work. And Dr. Aqsa Shabir just mentioned about Nature papers, which is indeed a big achievement for our group. And 2 of those papers are authored and co-authored by a Pakistani PhD student and postdoc, which is indeed a great achievement. And we are being awarded for our research collegiality and collaboration, which is key to all research successes. In 2022, Muhammad Ali Imran got Research Culture Award, and myself got Highly Commended Research Culture Award in 2021. And as I mentioned, we are the founding member of National Scotland 5G Centre, which was established back in 2019 by the Scottish Prime Minister. And our group is actively contributing to the national policy and strategies. We contributed to the 5G strategy for Scotland. And our applications of work are not limited to only one domain. Our applications are ranging from healthcare to mobile communication, to connected mobility, to teleimmersion and connected healthcare. So we have seen, not all of you, but many of us who are a bit older, they have seen that every 10 years, we have a new generation of mobile communication coming, starting from 1980s when we had 1G, and now we are in 5G. And with each generation, we have something new coming. For example, when 3G came, we started having mobile data. 4G, it is enhanced broadband. And 5G brought us a complete ecosystem of change where we have connectivity, not only connectivity improvement, but it provides an ecosystem which has connected everything. Because of it enhanced features like we have 1+ gigabits per second of bandwidth, ultra low latency, around 1 millisecond, and an advantage of connectivity for massive devices. And you will be surprised to know that as I started with that we are digital, we all are digital. So out of total population, 66.6% of population, which is around 5.22 billion, they are mobile users. And out of that, we have 4.66 billion people who are using internet. And this most internet usage is coming from mobile devices. And according to GSMA Intelligence latest report, there are, as I mentioned, 5.22 billion unique mobile users. And every user is spending 9.4 gigabytes of data I'm sorry, I don't know what happened. Can you hear me? Hello? Hello?
Yes, sir, we can hear you.
Yeah, okay, sorry, I don't know what happened. So, Professor Aksa, can you please check if I'm still live on YouTube, or I do need to do that again? Okay. I think I'm still, okay. So I was saying that with this pressure of connectivity of everything called Internet of Everything, it demands for a new network, because there are some challenges which 5G cannot fulfill, some requirements which 5G cannot fulfill. So this brings to a concept of new networks, which will be 6G, and it will have elements like ultra intelligence, machine learning based networks for AI mobile edge, intelligent mobile networks, an element like ultra broadband, terahertz communication, ultra high precision for robotic surgeries, aerial drones, ultra large coverage, so that we can have coverage in air taxi, in-flight mobile broadband, ultra high mobility to have connectivity in hyperloop and high-speed bullet trains, and ultra low energy, like to enable zero energy networks, which are the key enabler for improving this sustainable development goal around net zero. And these elements enable various use cases, like I told you that these elements, for example, ultra high precision and ultra massive connectivity will enable a use case of healthcare. For bullet train and hyperloops, ultra fast broadband and ultra high mobility will be the enablers. Now, the requirement for 6G are even stringent than 5G. So our requirement for 6G is in terms of enhanced KPIs, where we are demanding for a peak data rate, which is 2x of 5G. We want high resolution positioning, which is 2 to 3x of 5G, energy efficiency, 10x, and so on. Now the question is, who or what is the frequency band which can enable this 6G stringent KPIs? And the expected frequency band is terahertz, because if you look at the KPIs for 5G and 6G, 6G wants a peak data rate of 1 terabits per second, user rate of 10 gigabits per second, and latency of even less than 1 millisecond to enable use cases like holographic communication, extended reality, precision medicine control, and so on. And the features of terahertz, which will be the enabling, like you know that for 5G we use frequencies which is millimeter wave or sub 6 gigahertz, but for 6G we will be using terahertz because it has some inherent features, which includes it can enable us joint communication and sensing, it can provide us real-time network optimization, and so on. Now, whenever we have new technology, there are certain challenges which needs to solve. So one thing we found out that we need 6G because of the use cases we are looking for. And now the first question was, what will be the frequency band we will be using for 6G? The answers were, expected answer was terahertz frequency, but terahertz has certain challenges. What are those challenges? The first challenge is a very high atmospheric loss. Terahertz has a very shorter wavelength, and because of this shorter wavelength, it gets impacted by sand, fog, and rain. And this atmospheric loss is low at higher altitudes because there is no rain, there's vacuum. So it works very well, but at lower altitudes, like indoor, outdoor scenarios, we have this issue around atmospheric losses. And another issue is, as we move higher in frequencies, skin depth decreases. So the skin depth of metal in terahertz range, because we usually use metal kind of antennas. So the skin depth of metal in terahertz region is usually in the range of several hundred nanometers and is much smaller than metal wire radius. So when I say metal, it means iron, aluminum, and so on. And most widely used metal for antenna fabrication is copper. So terahertz copper antennas suffer from very high propagation losses and degradation in radiation efficiency because of decrease in skin depth. So this skin depth is a challenge because conventional metal, like I mentioned, copper and gold, they have low electron mobility. So this causes significant channel attenuation. So we need to look at some new kind of materials to enable wireless communication for these terahertz system or 6G system. So in our group, we are focusing on 3 pillars of research to enable future wireless communication. The first one is designing novel antennas at terahertz. Second one is intelligent reflective surfaces, which we call wireless on a wall. And the last one is sensing and communication. So because of time limitation, I'll just give you flavor of all these because we even couldn't accomplish all of these challenges, but we are working on this. World has started working on this. And I'm sure many of you will try to solve the challenges we are getting here. So this talk is more about giving challenges than giving solutions. So as a researcher, you are always looking for challenges to solve. So the first one is terahertz antenna design. As I mentioned that metals have issues at terahertz frequency. So you can see that what we are doing here is that we are trying to use 2D materials like graphene, perovskite to make these terahertz antennas. And these antennas are basically, according to John Cross, they are ears and eyes of wireless system. So we are trying to make these antennas by using 2D materials because these materials have superconductivity at terahertz and at nanostructure. No, these are the world first antennas you will not see anywhere. We have developed this in our group only. So we are privileged that we have James Watt Nano Fabrication Center and state-of-art measurement capabilities from 10 megahertz up to 1.1 terahertz. So by using our capabilities, we have designed various terahertz antennas. So the first one is a PICA antenna array, which was based on gold material with a ultra wideband performance. And the second one is CPW terahertz antenna array on a flexible substrate with dielectric constant of 2.2. And as you can see, that antenna has 4 layers, which includes gold, titanium, aluminium, and graphene. And the reason for titanium and aluminum usage was because we want to have a good attachment to the flexible substrate. And this third antenna is gold, titanium, graphene array fabricated on PET substrate, where it has 74 elements and resonant frequency is 0.85 terahertz. And this last design is a serial antenna array with 24 elements based on graphene and gold. And the resonant frequency is 0.8 terahertz. And these are the microscopic images you can see. Now, so I'll just highlight one of the antenna design. So the PICA antenna structure, which was the first one, it is a planar inverted cone antenna, which provides ultra wideband performance. It had 4 elements. And due to the flat profile, if you can see it's very flat, the PICA exhibits mechanical stability as well, due to which it is increasingly being used for, it will be basically used for commercial applications. And this array was used or was based on gold and was designed at 1 terahertz on a silicon substrate. So this is substrate, this is a gold-based PICA array, 1 cross 4 elements, as you can see. And the dielectric constant for the substrate was 11.9 with the height of 600 micrometer. And this design took us 3 years to fabricate because it includes various steps at James Watt Nano Fabrication Center that we took a silicon wafer, we clean it, we put it to PMMA resist, then we pattern the substrate. This is the pattern actually by using E-beam lithographic exposure. Then we did some development, gold deposition, and then we lift off to get the structure. And these are the microscopic images, and this image received Best Image Award recently from Metamaterial Network. And once we have fabricated, this is world first fabricated terahertz antenna at 1 terahertz. And we were the first one who were able to measure this as well, because it's very small in size, as you can see that if you look at this matchstick, so you can see the size is even smaller than that. So what we did that we used a probe-based measurement. This is a terahertz horn antenna, and the pitch separation of probe was just 22 micrometer, which was very, very small because we had CPW, coplanar waveguide fed mechanism, where we used ground signal ground probe with a very small pitch of 24 micron, which was placed, as you can see, on the antenna array to measure S parameter of antenna. And you can see that our simulation result agrees with the measurement because the expected S parameter was, it should be below -90 dB, so that we have 90+% efficiency. So in our case, the total efficiency of an array was around 80%, and the peak gain was, as you can see here, 16.5 dB. And there was some disagreement. As you can see, there are so many ripples in the measured results, and this is due to unpredictable reflection from the surrounding of the experimental setup, because at that such a small scale, it was so difficult to have confined environment. And the radiation pattern of this antenna was mostly omnidirectional, which was the requirement. Then the second antenna, which was graphene and gold based antenna, as you can see that it was a serial fed antenna, which had, if I remember, I think we had 24 elements. Yeah, we had 24 elements, and we used flexible pen substrate. The idea was that in future, we will be having wearable devices where we'll place this antenna. So sometimes you have to bend this as well. So we want an antenna which do not change its performance while in bending as well. And the outline feed was around 42 micron. So the antenna, as you can slide. Please request to mute your mic. Someone's mic is on. Sorry, I have to mute. Okay. So we found out that this antenna is basically independent of any kind of shape changes which we have done at various angles. And of course, we had to follow certain recipe which we had developed in James Watt Nano Fabrication Center for this design that we started by cleaning the sample with some kind of chemicals. Then we did transfer graphene, and then similar process that we did some spin coating, UV exposure, and then we did development of the design, and then we placed some gold resist and graphene, and then we did lift off finally to etch this design. And this was another design which I just mentioned to you earlier in the last slide. This is the design, and you can see the dimensions of an antenna array, which was 24 elements. And one thing we found out here was, which was very unique, that we tried to use hybrid material, that we looked at the antenna characteristics by making a single gold material, then we use single graphene, and then we did hybrid of both. And we found out that, as you can see, that when we use the hybrid material, the resonance was basically shifted. And if you remember, I mentioned that we designed it for a wearable application. So we tested this antenna on a 3-layer model, which is basically as the penetration depth of terahertz wave is so small. So we looked this antenna parameters by putting it only on the skin, which has 3 layers: stratum, corneum, epidermis, and dermis. And we tried to look at antenna performance in free space and on human body to see that if antenna gets any impact because of bringing it closer to the human body. Because what's happening there is that when you bring an antenna or a sensor which has antenna in it close to the body, the effective permittivity changes, because of which resonance change as well. So we need to optimize our design so that there is less impact from human body. And you can see that there is very less impact. The gain decreased from 8.8 dB to 7.2 dB. And radiation efficiency reduced from 80 to 60%. And the important thing is that there shouldn't be there was no shift in resonance frequency, but of course some change in S parameter amplitude. So this was all about terahertz antennas, which will be enabler for 6G. The second thing which we recently published Nature papers on, we call this concept wireless on a wall. So currently, if you want to improve the performance of your wireless system, what you do that you either make changes at transmitter side or you make changes at receiver side. But the new concept is that instead of making changes in transmitter or receiver, you manipulate the channel, you control the channel. So this is called intelligent reflective surfaces or wireless on a wall concept. So this example will clarify this in a much better way. That, for example, if I want to provide a quality of service to this user who is sitting here in the Hunterian Museum in University of Glasgow, the signal which is coming to this user does not have any direct path. So there are losses inside the wall coming from the building, reflection, refractions, diffractions, which are reaching to this user. But if on a wall, I place this reflective intelligent surfaces, what they will do, or what we can do with that, that I focus the electromagnetic wave towards that user, which will ultimately improve the channel quality and the quality of service to the user. So they come with different names, software defined meta surfaces, reconfigurable intelligent surfaces, intelligent reflecting surfaces. And this is another very good example. So for example, if I want to provide coverage to this user from a base station, and there's an obstruction, a big building in front of it, how signal will be reaching to this user? It is going from mobile base station, reflected from this building, and there is some reflection which reaches to this user. Now there are two solutions to solve this problem. First one is I put a repeater here to enhance signal quality so that it reaches to this user. But second one is, if I use this concept wireless on a wall, I put these materials are intelligent reflective surfaces on a wall. What they will do that they are passive surfaces, so they will focus the beam toward the user. So with a very less cost, because repeaters cost a lot, you can improve the quality of service. And their applications are immense, starting from train stations, airports, flights, healthcare, stadiums. And the application we are working on with them is basically healthcare. So the idea is that we have ambient radio frequency signals around us, which is Wi-Fi signals, mobile signals, radar signals. So the idea is that how, without using wearables or any devices, you monitor people's health. And health can be monitored with two indicators or two parameters. Whenever you go to doctor, they measure your vital first by putting something on your body. But our idea is that, can we measure those vitals while a person is sitting in her or his TV room or sleeping without using any kind of sensors on a body? And the other indicator is for elderly people, detection of fall, your gait or walking pattern is linked to disease in future. So what we are trying to do there is that those mobile signals or Wi-Fi signals are scattered. So of course we can use them to look at these healthcare parameters. But what if we want to increase the resolution? That can be done if we install these intelligent surfaces on a wall, and then we can control the beam, and then we can focus the beam on a user, and we can not only measure that user with high resolution, but we can track that user as well. So we designed these intelligent reflective surfaces test bed in our lab. So this is one of the intelligent reflective surface tile. So we say this a tile-based structure, and each tile has a small unit cell. So we have designed this in a way that we can get a phase shift of 0 or 180 degree. So how these intelligent reflective surfaces works is that, as I mentioned, that we control the beam. What I mean by control the beam, so whatever I am transmitting one signal and Y receiver is receiving some signal, what is happening? There are some direct signals coming to her or him, or there are some reflected signals. So what is happening at the receiver side, those signals either combine constructively or destructively. And that destructive addition is due to the phase difference. So with these surfaces, what we do that we manipulate and control the phase so that they are aligned and we have constructive addition at the receiver side. So we made this one tile And then the requirement was that this tile should be low power, low cost, and should be scalable with a very high switching speed. So the tile we designed had a very high refresh speed of 130 kilohertz with a power consumption of 1 to 3 watt. So our one tile had a dimension of 33 cross 33 centimeter with 256 unit cells. So we have no flexibility to put these tiles either in square shape, in rectangle shape, in whatever shape we like. So we made 9 of these tiles, and then we made our test bed. As you can see that this is our 1-bit IRS test bed, which has in total actually 16 tiles, and the total dimensions were 1.5 cross 1.5 meters. So this is our complete test bed. You can see that we can use that for basically branding as well. We did that. So this test bed had in total 4,096 elements, which we were controlling with a shift register and pin diodes. And each element had basically current drawing of 2 milliamps, which result into total power of around 15 watt for the whole unit. So when I mean 1-bit intelligent reflective surface, it means that you can change the phase of the signal by only 2 states, either 0 or 180 degree. But there are some requirements where we need to change the phase more often. For example, if some of the user is at 45 degrees, some is at 90 degrees, so I need to focus the beam in 45, 90, 135, 360. So for that, we design another intelligent reflective surface hardware, which can have 8 different phase states with the phase shift of 45 degrees. So this is our 3-bit test bed, which use the same approach of having multiple tiles. In this case, it was 6. So the total dimension of the test bed were 1 cross 0.7 meter, and the total unit cells were 2,300. With, of course, there is some brain behind it, where we were using an FPGA and Raspberry Pi to control the switching on and switching off of diodes, which enables any of the unit cell. So this is the test bed for 3-bit. And then whenever you design these kind of surfaces, you try to measure their reflection responses. So we did measure reflection response in our anechoic chamber. And there was a very good agreement between simulation and measurement. No, we have done it. What is the advantage of this? We need to prove that. So what we did, in order to prove that, we did various indoor experiments. So one of the advantage for these surfaces is, for example, in your basement, there are no signal coverage. So what you can do, you can put these surfaces on your window. So what these surfaces will do, they will focus the beam inside your basement so that you can have very good signal coverage. So we want to see how much signal coverage we get. So we designed various experiments in our school. So we considered various scenarios in a lobby area where we place transmitter at one corner, receiver at various locations, as you can see. And then this reconfigurable intelligent surface was placed in a corner. Then we tested the corridor scenario as well, which was L-shaped, transmitter here, receiver at various locations. This reconfigurable intelligent surface was placed in the corner. And then we tested the multi-floor scenario as well, which was very important, which was close to reality, where transmitter was on floor 1 and receiver was on ground floor. And guess what we found out was a breakthrough that we get a signal improvement of 40 dB, which was humongous. And the idea is that in future networks, you do not need to deploy expensive hardware. You just put these surfaces either on a wall, either on a window to enhance the coverage of the signal. And as I mentioned, the applications are immense for this scenario. So I think this video will clarify the concept better, what I meant by this signal improvement. So we have a short video which will show what we did.
I'm Captain James Watt School of Engineering and also Deputy Head for Communication Sensing and Imaging. In this video, we will show you a video streaming demonstration of an intelligent reflective surface. Reflective surface have been developed in University of Glasgow. It has more than 2,000 unit cells and it is working in sub-6 gigahertz. As you can see in the screen on the right-hand side, at this stage, our IRS is not working and the signal quality is so low. So now we will configure our IRS. As signal quality is so low, video is not being streamed. So as soon as we have configured our IRS, you can see that signal strength is going up and then video streaming will start. And our signal quality is increased by around 25 dB.
So as you have seen that how video was being streamed. So this is another demo.
Reflective surface with around 4,000 elements, which is scanning the beam in complete 360 degree in free space. As you can see that wave is rotating from 0 degree to 90 degree.
So what we did was a very interesting thing. So this was basically the second part. And I would like to show you a very brief result, which we recently published in Nature, which was basically, now I told you that these intelligent reflective surfaces have so many applications. So one of the application we picked was contactless healthcare. So we wanted to prove that these surfaces are this wireless on a wall. We call it wireless on a wall. WOW concept can help us to enhance resolution and tracking in contactless healthcare domain. So I explained to you what is contactless healthcare, that instead of using wearables, instead of using any kind of sensors, what you use already available network, which is Wi-Fi or mobile signals in your home, in your environment, to monitor people heart rate, to monitor people breathing rate, to monitor people walk pattern, to monitor people fall. So what we did was that we tried to see, we have done a lot of work on this, so I'm not talking about that. So what we did was that we placed transmitter in one room, receiver in another room, and this IRS in the corner. So what we did some experiments on a multi-floor scenario as well, transmitter on first floor, receiver on second floor, and then user performing some activity. So transmitter, receiver were totally none of line of sight to each other. So what we achieved was a breakthrough that when we didn't have any IRS surface, this intelligent reflective surface, the classification accuracy was just 53%. And when we tuned these surfaces, the classification accuracy for activity, a user was performing various activities like sitting, standing, walking, and we achieved a classification accuracy of 100%, which was indeed opening of a new door in this research domain. And this was actually our wireless on a wall concept, that what we want to do is that in future, we are going to have homes which have all kind of sensors available, which includes RFIDs, temperature sensors, point of care devices, nanoscale sensors, and they all will be collecting information together, which will be sent securely to the cloud, which will process data by using machine learning or deep learning. And then care provider or a doctor will look at that answers, and then they can provide a feedback to the user that, hey, look, you are going to have some kind of anomaly in next 12 hours. So come to the hospital. So this can enable independent assisted living. So this is where we stop for the second scenario, which we are working on. Third and last one is how we can have sensing and communication together by having this new domain of 6G and terahertz. So back in 2015, we proposed a concept. So the idea is that in future, what will happen that we have a single capsule which we will swallow, and that single capsule will have 100,000 of nanosensors in it. And those nanosensors, once I eat the capsule, those nanosensors will spread inside my body. And then they will measure either cell temperature or biological changes or chemical changes, which can be fed out of my body. And then we apply some kind of signal processing to do proactive detection, that before some disease occur to someone, we can detect those, because there are certain molecular changes occurs inside our body before there is some kind of disease attack. So we basically started working on that 8 years ago, that how those nanosensors, which are not out yet actually. That's why I told you that whatever I'll be talking to you, probably many things will not have impact currently, but in next 5 to 10 years, these will be the futuristic directions. So we developed basically some channel models, some link budgets for these nanosensors, that what will be the requirement at terahertz frequencies for these nanosensors. So we proposed the world first channel model, which takes into account number of sweat ducts inside our body, the distance between the transmitter and receiver, and the frequency at which we will be working at. And then another interesting thing we did was that, how, because global population is increasing and there's a food shortage, and at least 30% of the crops are being destroyed by some kind of disease. And farmer come to know about any kind of disease or insect attack when damage has already been done. So our idea was, can we do this proactively? Proactively means that before it happens. And these plants have immune system like us. So if your immune system is weak, disease attacks. So similarly, what we were trying to study by using this terahertz and futuristic 6G network, that can we detect proactively any kind of anomaly in plant leaves, which can help farmer to take some proactive decision. For example, look, your crop need water in 20 days. So if we can tell that farmer, he or she can take decision, or this insect gonna attack, put some urea. So what we did, that we used these terahertz waves and systems basically to look at the water content inside the leaves, and we detect this water content estimation with an accuracy of 95% by applying machine learning. So we looked at 14 different kind of leaves. We tried to do the time domain spectroscopy. We applied machine learning to the data, and we found out that yes, we can do that. This has a great potential. And these are some of the results. Because of time constraint, I'll not go in detail, because the idea was just to tell you what can be done. And then I think I'll try to wrap up that what we can do with this terahertz and 6G in future. This is an interesting futuristic work we are doing, that in future there will be an holographic communication. And you are seeing this in television, actually, that there is some kind of holographic communication, that you teleport someone. But what we are doing is something very unique. Up to now, we can communicate 3 senses. So humans have 5 senses. So up to now, we can communicate 3 senses, which includes hearing and vision, which is basically you can have both audio and video call with a mobile phone. And third one is haptic feedback. So you have seen robotics sensors where you can get shocks in your hand if someone is doing something at other side, which is called haptic feedback. But there are 2 senses, which is smell and taste. Smell and taste, which is not communicated yet. So what we are trying to do is that how we can communicate all these senses from point A to point B. So what about, I want to eat biryani in Glasgow right now in my office, and I want biryani made by my mother's hand. So what I'll do, I will, this is just a concept we are working on. I'll wear VR glasses, and then what will happen, that there will be certain neurons inside my brain which develops that taste bud. So the user at B side, they will tell me basically that Z kind of neurons get activated. So I have a stimulator which will stimulate those neurons, and those neurons will be stimulated in my brain, and then they will flow inside my body to give me a feeling that I'm eating biryani. So taste and smell both will be communicated as well. And see, its advantages are immense, because I want to reduce my weight. I want to eat biryani as well. So you can do that as well. So for that, you need ultra reliable communication with very, very high bandwidth and ultra low latency, which can be enabled only by 6G. So this is just the concept we are working on, and hopefully in some time we will be able to do that. So I think without going beyond my time, so the summary for my talk is that 6G has a potential to revolutionize the future from various perspectives, to enable various use cases, which but there are so many challenges which needs to be solved, and there are various enablers we are working on, and hopefully in 10 years time you will see all of these. So if you are interested to know more about it, we have so many books in this area, so many conferences and events we organize, where you all are very welcome. And of course, I would like to add very important thing, that success is always a group achievement. And I would like to thank all my colleagues, students, funders, which enables us to do this kind of research. So thank you so much. I'm open to any question, answers. So if you have any question, you can either type in the chat, or you can unmute yourself and ask a question. So I have opened the chat. So any question?